Hello, modern algebra class. It's been a little while since I've seen you. Hope you had a nice spring break. I promised you that I would give you a reminder of what we've been doing, and Sophie, of course, wanted to help with that. So let's just do a quick recap of what we've been doing all semester and where we'd like to go. Right, Soph? Okay, Sophie's ready. All right, here we go. At the beginning of the semester, we started by talking about polynomials and polynomial equations. Hey, and what it means for something to be solvable by radicals. Which is another way of saying it has its version of the quadratic formula, right? We can find some formula for the roots involving nth roots, addition, subtraction, multiplication, division, all that good algebraic stuff, but we're not talking about trig, right? No trig functions, no sines, no cosines need apply. And so our big question is, why no quintic formula? And I'd like to tell you, as we go through what we've done, how this is all going to build together into the answer to this question. So some of the things we talked about right after we talked about our first question were things like complex numbers. And in particular, for those complex numbers, we talked about the nth roots of unity, which look like cosine 2 pi over n plus I sine 2 pi over n. We have a geometric interpretation of those sitting on the unit circle, blah, 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 blah. Anyway, so we've got the complex numbers. We also have modular arithmetic, modular stuff like z mod n, right? The set of equivalence classes of remainders when you divide by n. And that was where we launched into our bigger discussion about fields. So one of the major algebraic objects that you see in your first course in modern algebra is the field. And the field has all the axioms, all 10 of those axioms. We've got addition, multiplication, at least 2 elements. My pineapples are getting in the way here. All right, we've got at least 2 elements, addition, multiplication, the axioms A1 through A5, M1 through M5, and then our distributive properties D1 and D2. And I'll remind you what those are. I'll put those in the description for this video. But we've got all of these axioms, right? We're closed, we have identities, every element has an inverse for multiplication, has an inverse for addition. We've got the distributive property, life is good. So we've got fields. And the complex numbers are a field. So an example, the complex numbers, more relevant to our discussion is the field of rational numbers. And then we've got the field of rational numbers when we start throwing in algebraic elements. And so these algebraic elements, remember, are just roots of polynomials with rational coefficients. So we've got algebraic elements. And it's these fields in particular that get us closer to answering our question, why no quintic formula? We're going to start to understand what's going on when we adjoin elements and how can we move them around via automorphisms. But before we get there, we also talked about rings. So rings, like fields, have a bunch of axioms. They have 2 operations. They're non-empty. Maybe they only have 1 element, in which case they're the boring 0 ring. We've got rings. We've got A1 through A5. Every ring has all of the addition axioms. We've got M1 and M2. That's closure and associativity. And we've got D1 and D2. So notice what we're missing. We're missing, oh, actually, I think we also have M3. No, we're missing M3. M3 is that we have a unity. So if I say a ring with unity, I mean there's an element that acts like 1, the multiplicative identity. We're also missing M4, which are the multiplicative inverses. So if we have a ring with unity and every non-zero has a multiplicative inverse, then what we're talking about is something called a division ring. And if we throw in commutativity of multiplication, which is M5, we're talking about a field. So we had a whole bunch of different types of rings. We had some important ones are integral domains, And among those really important ones, which we'll talk about really quickly later, are the PIDs, the principal ideal domains, which means every ideal in the ring looks like it's generated by one element. So if I have a principal ideal domain, I grab an ideal, there's some element that every element in that ideal is divisible by, and that's our generator. So integral domains are important to us, and in particular, principal ideal domains. And then we saw other sorts of weird examples, like non-commutative division ring, we've got the quaternions and stuff like that. Okay, so we have fields, we have rings, we have the handful of theorems that go along once you define an algebraic object. You've got the properties of that algebraic object. You've got the definition of what it means for something to be a sub one of those things. You've got the theorem that says here's the quick and dirty way to prove it. You've got the definition of a homomorphism, which is a way of saying these two algebraic objects are similar or compatible with one another. The algebra works out. And in particular, we've got for fields, we've got some additional structure. We talked about the vector space view of extension fields. And what I mean to say there is that we can look at Q adjoin the roots of some polynomial as a vector space over Q, and more generally, we understand how to write it down. So when I say there's a formula, I mean there's a formula for writing down a general element. And so, for example, this is some of the stuff that we talked about more recently in class. If I look at Q adjoin, let's say, oh, what do we want to throw in first? Let's throw in, let's say, square root of 3 and I. Those are going to be the roots for my polynomial p of x will be x squared plus 3, right? I can write my roots in that way. At least it's contained in there. We could think about whether or not it's equal later. So if I look at this particular element, I know that the minimum polynomial, so I can do one of my field diagrams, right? So I have Q adjoin square root of 3 over I. I've got, let's do square root of 3 first so that we can use Eisenstein's criterion. So as we work these out, we think about the minimum polynomials in order to figure out what the dimension of this vector space that we're going to build will be. So here, my minimum polynomial for Q adjoin square root of 3 over Q is the polynomial we started with. It's x squared plus 3. It's irreducible by Eisenstein's irreducibility criterion. The prime that I use is 3, and it has degree 2. So as a vector space, Q adjoin square root of 3 is a two-dimensional vector space over Q. And then I think about the minimum polynomial for I have x squared plus 1. Now here I've got that the minimum, plus 1, sorry. I've got the minimum polynomial here has degree 2 as well. This is irreducible by some proposition. I think it was proposition 8.12. Its roots are plus or minus I. The field that we're looking over here has no imaginary elements in it. It's got only real elements. And so these roots don't belong to this field. It's a degree 2 polynomial. If it factored, it would have to factor into degree 1 stuff. The factors would involve the roots. Alas, irreducible. So here we see that this is another two-dimensional vector space. And so the whole thing is a dimension 4 vector space over Q. And we know how to write down the elements. We can write the elements as, oh boy, did I leave myself enough room? I guess we'll find out. We can write down the elements as a plus b square root of 3 plus c plus d square root of 3 with an I there, and a, b, c, and d are in Q. And the way that I did that was I know that this field has elements that look like a plus b square root of 3, where a and b are in Q. And the way that I worked with this one is that this looks like alpha plus beta I, where alpha and beta come from Q adjoin square root of 3. So I'm just popping in those elements up above. Q adjoin square root of 3. Okay, so we've got this idea that we can think of this as a vector space, Q adjoin square root of 3 over I, and I over Q is a 4-dimensional vector space. And this number 4 is going to tell us something about automorphisms of fields that fix our base field Q. And that's where we're headed next. So, okay, we've talked about these algebraic objects. We've got a way of understanding extension fields in terms of these algebraic elements that we're throwing in. Why do we care about algebraic elements? Well, that's what we use to make something solvable by radicals, right? Algebraic elements are things that are roots of polynomials, and so they're going to involve nth roots and addition and subtraction and stuff. So what's coming up next? Well, sorry, I've got inconveniently placed furniture in my home office. You have to excuse the lean here. We've got automorphisms that fix a base field. That tells us about how we can cycle different roots around. It tells us that if we're fixing our base field, often it's going to be Q or Q adjoin some stuff. If I know how I can move the roots around, that tells me something about the structure of the roots of the polynomial. And the way that we're going to understand this object, this is the most important definition relevant to solving this, or to answering our big question, is, let's see, I want more dramatic color. Hold on. Let's find something good. Okay, we're going to talk about something called the Galois group. Now, if you remember, solvable by radicals as a definition sucks. It's really hard to work with. I mean, I guess it's okay if you know something's solvable by radicals, you can go ahead and show it using the definition, but it's hard even just to show something solvable by radicals, and it's almost impossible to use the definition to show something isn't solvable by radicals. And that's because the definition is saying there exist some things. To show something's not solvable by radicals with the definition, you would have to show that every possible choice fails, and that's hard to do mathematically. So what we're going to do instead is we're going to look at this thing called the Galois group, and we're going to try to figure out a way to learn something about a group that has to do with the roots of the polynomials to answer the question, if this group has property blah, 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 then our polynomial is solvable by radicals. And if it doesn't, then our polynomial is not. So this is our main mathematical machinery. And to get to this definition, we use fields and rings, and we'll talk about this third algebraic object called a group. This is actually kind of cool. It's a cool way to see your first semester of modern algebra because it brings in all of the things you normally see to get to this definition. So what the Galois group is, and we'll see more about this when we get into it, is it's the set of automorphisms. Let's say F is an automorphism from a field K to a field K. F is an automorphism of fields. That fixes a base field F. So somewhere in here, I've got F contained in K is an extension of fields. So this set of all of these operations, or all of these automorphisms that send K to itself in a way that preserves multiplication and addition so that it's a homomorphism, is one-to-one and onto so that it's an isomorphism, and again goes from K to itself, so it's an automorphism that fixes our base field F. These elements are they form what we call the Galois group. And so we've got to talk about a third algebraic structure called a group. Now, groups, as opposed to rings and fields, only have one operation. And I like to call it star. Sometimes it's just written like multiplication. They're non-empty. And they satisfy 4 axioms, G1 through G4. Now, based on what A1 and A5 and M1 through M5 are, you can probably guess G1 through G4. We've got closure, we've got associativity, we've got an identity for the star operation, and we've got this, we've got inverses. We don't need to worry about non-zero elements because zero doesn't make sense if we only have one operation that we're talking about. And what we'll show is that the Galois group, we've named in this way, with the operation function composition, is one of these things called a group. And then the last part of the course is defining this thing called a solvable group. And we'll see that if the group that we're talking about is one of these Galois groups, it's solvable if and only if the polynomial that we're interested in the first place is solvable. So we'll see solvable groups are related in this really nice if and only if way to solvable by radicals polynomials. And so what we're going to do then is we're going to say, I'm totally giving away the punchline here. If you want to stop the video now and live in suspense, that's totally fine. If you'd like to know where we're going, we're going to find P of x, Q bracket x of degree 5 with Galois group S5. Now you don't know what S5 means yet, but it's the name of a particular type of group that we're going to talk about really soon. And then we're going to show that S5 isn't solvable. And therefore, our degree 5 polynomial isn't solvable by radicals, which means there's no general quintic formula because we found something that we can't build that formula for. And that's the plan for the rest of the semester. Now, I know there's a lot more that went on earlier in the semester. I'm going to do my best, since we're in the middle of the COVID-19 pandemic, to strip this down to the most essential elements so that you still get to enjoy this beautiful story with maybe a little bit less of the stuff that I hoped we'd get to see in person. All right, peace everybody. I miss you. It's very weird on campus without all of you. I hope you're safe and healthy. If you have any questions about this video or anything that's going on in the course, reach out through Piazza, and I will see you soon, virtually.